Yes.
Yes. So I'm excited to introduce Xiaohong Chen from, he's CTO at Pi Squared, and he's going to talk about K. And we are happy to have him today, and looking forward to his lectures and lessons and things that we can learn from him. And you have 25 minutes, including Q&A. We do not have a clock, but let's go. And
here.
Please give him big hands.
Thank you. Yeah, thank you, everyone. So it's very happy to be here to talk about programming languages and why they must have formal semantics and what we can get out of the formal semantics and so on. So I'm Xiaohong Chen. I'm currently the CTO of Pi Squared, a new startup focusing in the blockchain space. Before that, I got my PhD from UIUC. So a lot of the work I presented here is the work that I did in the UIUC and the work that I existed before I even entered the UIUC. It's a long history of serious work on this topic. All right, so I'd like to give a very prompt start. Just remind you how complex software systems are today, and basically they're everywhere, right? So they're everywhere in our daily lives. So they're in autopilot airplanes, banking systems. You find them in cryptocurrencies and smart contracts, AI agents, and so on. So needless to say, these complex systems create higher needs for program correctness. But the other side of the equation is that the way we manage and organize programming language design implementation makes it actually harder to establish that correctness. So let me explain. So how do we approach PL design and implementation in the state of the art? Well, we pick a language, say Java, and we pick a tool that we want for the language, say interpreter. And then we spend years and years and a lot of effort, right, to develop an interpreter for Java. And then, yes, great, now we have an interpreter for Java. But how about the other tools, right? So, as users may want to have a formal verifier for Java. How do they get those? And how about the other languages? Are we going just to repeat basically the same procedure for each and every combination of a language and a tool? So are we just going to do that? Unfortunately, yes, right? So that's what we do today, right? So we pick a language, we pick a tool, we consider each and every possible combination, and we implement a specific tool for a specific language. So naturally, it results in higher cost because we need to design, we need to develop, we need to maintain L times T different systems, right? Because of this, you have this quadratic effect going on here. And there is an enormous amount of duplicated work in this scheme. And programming languages become hard to update if you do the tools this way. Why? Because imagine now you want to add a new feature to Java. And imagine the amount of work you have to go back and change all the related tools, right? So that's a big effort, right? So actually programming languages become reluctant, right, to embrace new features if you do the tools this way. And it's very hard for the tools of the same language to stay in sync with each other as well, right? So what happens very usually is that when a new version of the language comes in, the core most critical tools like an interpreter and or a compiler is immediately updated, but all the other tools like the verifiers or model checkers, they start to deprecate it. Why? Because no one is there to maintain them, to update them, and so on. So this is kind of the state of the art, and what we like to do here is to take a step back, right? Look at this problem and just see, is there a better way to approach PL design implementation? So this is what we believe how PL design should be, right? So let's still take Java as an example. So yes, we have Java, and the first thing we should do is define it formally, which means that we want to have a formal semantics of Java. So I depict it as, as a very big circle to illustrate that the formal semantics itself can be a very complicated artifact, and it can actually take no less time to develop than, say, an interpreter for Java. So it's a big effort. Why? Because this formal semantics is a complete, rigorous an unambiguous mathematical definition of Java, right? So it defines all the behaviors of all Java programs out there. So it's a very comprehensive artifact if you think about it. Now you may ask, what's the point of spending a lot of effort defining it? Well, because once you have a formal semantics of Java, then in principle you have all the information to do these tools. So you don't need to implement the tools by yourself. All the tools can be derived in a fully automatic way from this formal semantics of Java. So as you see here, right? So we can derive from the formal semantics of Java all these tools, interpreter, compiler, a model checker, and so on, fully automatically. So this formal semantics serves as the fundamental basis of correctness. And of course, we can extend this vision to all languages out there. So whatever programming language we want to do, define their formal semantics, which is a complete, rigorous, unambiguous mathematical definition of all the behaviors of all programs of that language, and derive all the tools automatically. So the advantages of this approach are clear, right? So instead of higher costs, now we reduce the cost significantly to L plus T systems, right? So each programming language has its own semantics, which, as I said, is a very complicated artifact. So that's L systems out there to maintain, to develop, and each tools is now parametric, right? Because that interpreter right there is actually a parametric interpreter. It takes the formal semantics of a language as input, right? So basically, we're talking about T parametric tools, language parametric tools. So only L times T system out there, right, to consider, to maintain. And by doing so, we reduce the duplicated work via these parametric tools and also the reusable semantic modules, for each languages. Now languages becomes, instead of hard to update, you can actually plug and play your language, right? All you need to do is to define the formal semantics of a language using a tool called the K-framework that I'm going to explain later. But you can really plug and play your language, and this is extremely convenient if you're doing your own language. For example, if you're designing your own DSL, right, for your domain. So this is very helpful because it helps you to get a prototype of your programming language very quickly, right? You don't need to worry about implementing manually, right, a compiler or interpreter or the verifier, right? If you care about correctness, you don't need to do that manually, right? So all you need to do is to look at your programming language as a language designer, right? You care about its features, you care about its behaviors, and you formalize all of that as its formal semantics and let some automatic language framework do the rest for you. And finally, because because tools are parametric in the formal semantics, they are automatically in sync, right? For example, interpreter and compiler here, they are based exactly on exactly the same formal semantics of the language, right? So they're correct by construction. And for example, if your language change, if you modify your language, all you need to do is to push one button, regenerate all the tools, and you're up to date. All right, so this is how we think PL design and implementation should be, right? So we call it semantics first approach, right? So whatever thing you want to do, define the semantics first, and then everything else follows later. So to give you an idea how a formal semantics of a language looks like, right? So so this is the K framework. So all that I said have been accomplished, right, by the K framework. So I'll be explaining K later. But basically, how does a K definition look like? So just to give you an intuition, so this is the complete K definition of kernel C, which is a fragment of the C language. Of course, it's sort of like a graphic representation, so it's kind of like automatically generated from the text version. You type the text version, and K has this tool which generates this LaTeX-ish, with the graphic representation. But this is actually a formal semantics, right? It's understood by machines. You can actually generate, correct by construction tools out of it. The point here is to show you that you can actually fit the formal semantics of language in one slide. Of course, you probably cannot read it. We'll zoom in a bit. But what happens here is that, so in the first column, you define the formal syntax, okay, of the language. And in the second and the third column, you define what is called the semantics. So let's zoom in a bit, right? So look at the syntax. So syntax, not very exciting. It's defined using BNF with annotations. So for example, here we're defining the syntax of expressions. And this particular grammar rule is for assignment, right? And you have this blue annotation. And there are many annotations in K. So this particular one is about evaluation order, right? Saying that the evaluation order of an assignment is strict on its second argument, which means that I want to evaluate the second argument, the right-hand side, first to a value, and then go on. So basically from the syntax, right, you have a parser. And just to make things easier, we allow people to write annotations like this one to specify some useful semantics of the syntax. Like this one is about the evaluation order and so on. So once you have the syntax of the language, the next thing you want to do is to think about the configuration. So a configuration is essentially a state, a runtime state of the program, when it's being executed. So it's consisting of all these little pieces called cells, semantic cells. Each cell holds a specific type of semantic information. So for example, all the cells are aggregated in this top level T cell, and within you'll find individual cells, like the K cell, one of the most important cells. It holds computation. K stands for computation. Basically the code you want to run. And the code starts to change, starts to evolve as we execute it. And in order to execute the code, we need to also have other cells like the function definitions, the environment memory, the function stack, input and output, and so on. Right? So you figure out what semantic cell should be part of the configuration of your language. And then the rest of the work is just to specify how a configuration should go to the next one. Right? So basically, that's a formal semantics of a language. It's a transition system over configurations, over the state of a program. So the way we do that is like this. Again, so on the top is the graphic representation. In text, you will write something like this. So this transition system is given by semantic rules. And this rule is for assignment. Okay, so let's read the graphic representation. They're identical, right? So basically says, if I have a configuration where in the K cell, the first computation is an assignment. So X is assigned to V. V is a value here. And in the environment, X is pointing to some value which I don't care. Right? So that's what the first line says here. So if this pattern is matched by my configuration, then I rewrite them in the following way. I will write the assignment expression into the right value, V, because that's the semantics of C. Right? The value of assignment expression is its right value. And I will write the value that X points to in the environment cell also to V. So this is this step. This is a rewrite rule, and each step defines the semantics of assignment, basically. And look what's interesting here, and I think this is one of the critical innovation of K, is that you don't mention anything that you don't need here, right? So literally, you just mention the K cell, because you need to know it's an assignment, and the environment cell, where you need to do a rewrite there. So you don't need to mention any of the other cells. So semantic rules are given contextually here. And the benefit of that is it makes semantics modular. So imagine I have C, and I start to add new features. Like I want to add threads. Let's make this kernel C multi-threading. Cool. Well, in order to do that, I need to add semantic cells holding the actual threads and so on. So I'm expanding my configuration of the language. But this rule stays the same. It doesn't need to change. Why? Because it only mentions the minimal fragment of the configuration that it needs, that it cares for this particular assignment expression. Right? So imagine you have more cells going on. the exact same rule stays, right? You don't need to go back and change existing rules. So this is, I think, one of the most important engineering techniques that really make K scalable, because it allows you to define the semantics of a language in a modular way. Okay, we need to move faster here. Yes, yes. Yes, go ahead.
Sorry, yeah. Because you mentioned concurrency as an example. So once I have concurrency, I will have more than one K cell because there's multiple threads. I will have more than one env cell. I have one for each thread. I might even have one for each stack frame. So something, somewhere has to define, like, it's not unambiguous anymore in itself, right? There has to be something somewhere which deals with the fact that, like, I have to match up the threads
same
with the environments and
exactly.
things like that. So this can't be as easy as just leaving it unchanged. So how do I deal with this in a
That's a very good point.
setting?
So basically, what happens here is that K has this. In order to figure out how to put together the pieces of the cells here. So K has a configuration completion algorithm, and it will take into account of what you just said, right? So for example, if I have a semantics of multi-threading language, which means that my configuration will have multiple K cell and environments and so on, each for each thread. If I just write the rule like this, K will know that I need to find a K cell and environment cell that's as close to each other. So they must be within the one thread and so on. So that's taking into account of the configuration completion of K. If you want to you can control it. So if you want the flexibility to, I want to match a cell in K and another environment cell in another thread, what you need to do here is to specify that, right? So you'll be wrapping around this K cell with a thread cell, and you will wrapping the environment cell with another thread cell. So K knows that, I'm looking for two different thread cells. One should have this code and one should have that environment, if you want that feature. Right, but by default, if you just provide a minimal example, K gives you the expected behavior, right? But that's a very good question. Yes, yeah, thank you. All right, so, okay.
Sorry, how are the side effects handled?
Sorry,
side effects.
Oh, side effects? So, side effects, you mean, for example, so basically, this is, so for example, if V here, somehow is an expression. So the reason why there's no side effect here is that V is a value, right? Because, for example, you may have a side effect where V is, for example, x++, in which case you must evaluate x++ first, because that is the, if you remember, right? So this is what this annotation means. When you evaluate an assignment, you want to evaluate the right value first, which means that before you get to this rule, you will get to the rule that tells you how to evaluate x++. And in that rule, the side effect takes place. Because to evaluate x++, you will need to find where the x value is and update it, and so on. And then you get a value and do this assignment. So basically, side effects are also defined as rewrite rules. Right? Because at any time, so the point is each and every semantic rule here is a transition step from one configuration to the next configuration. So in principle, right, so you have the entire configuration of the program in hand. So you can specify whatever side effects you want to do on that configuration. The fact that you don't see the other cells is a feature of K, because they don't change, right? But if indeed some side effect happens and something should change, for example, you have a counter. You may have a counter saying how many assignment statements have been processed, right? So in that case, there should be a side effect where you have a separate cell holding the counter, and you have to increment that counter. So in which case, you will add one more line here saying the side effect. Yeah. Okay, wonderful. Thank you for the question. So, right, so moving on. So, so just to give you an idea, so this is the complexity of a real world C language. So it has 120 cells, plus more than 5,000 rules, semantic rules, we just saw. So I think this is the kind of, finding that makes us believe that any formal semantic framework must be executable, right? Because we are talking about the definition of a language, right? The semantics of a language is the definition of a language. And we have a definition of this complexity. And how do you know that definition is correct, right? So you cannot prove it. It's not like a theorem. It's a definition. So the only way to do that is to do massive testing, right? So you run the definition against a lot of test programs, and you see whether the results are expected. So if your formal semantics is not executable, then most likely it has bugs that you don't know, right? So so basically that's our firm belief, right? So formal semantic approach must be executable, with the only exception that you may work on a correctness proof against an executable model of the semantics. But you have to, essentially, this is the only practical way to the correctness of a definition. Okay, let's moving on. So I think I will skip this very quickly because we're running out of time. So let me show you. So this is basically K in practice, right? So you see that a lot of pretty complex languages have been defined in K, especially the blockchain languages these days and so on. All right. So I want to spend maybe 2 more minutes to talk about some recent progress on K. So basically, people have asked this question a lot. So what if K itself has bugs, right? How are you going to do that? So a very recent work here is to focus on making K trustless. So we don't need to trust K, right? So we hear that trustless is a good word, because think about that means you don't need to trust it. You kind of eliminate K from the trust base. So the challenge here is K itself is very complicated. So it's more than 500,000 lines of code, many languages, complex data structures. Of course, it has bugs. And of course, you don't want to trust it. You don't want to take the correctness of K for granted. So, but it's very hard to verify because of this complexity. So the idea is to try translation validation, which means that let's find a logic and use that logic to formalize K, so that everything you define in K, every semantics in K becomes a logic theory. And everything that K does has a logic proof. So I don't care whether K is correct if I can check the proof. And I can check the proof using a very small program called the proof checker. So this is like a way to eliminate K, right? So making K trustless. You don't need to trust K anymore. Instead, you require K to give you a logic proof of everything that it does, and you check the proof independently, right? So, and if the proof checks, then you know that K is correct. So, for example, right? So this is how it works on C. So if from the C semantics we can do a C interpreter which can execute programs and give you some output, right? So for example, this is a very simple program that calculates a total sum from 1 to n, and the K interpreter will say that the value S is yes 50-50. But you don't want to trust that. In this case, you might. It's simple. But imagine this is a smart contract, right? It holds like millions and billions of dollars. You don't want to simply trust K on that. So what you can do is to get a logic theory out of the C semantics and encode this particular execution trace of your program as a logic formula. Now we have a logic theory and a logic formula. What connects the two is the logic proof. So we find a logic proof and check that automatically. And if the logic proof checks, then K is out of the picture, right? So now the trust base is reduced to this very simple proof checker. So I think I will stop here because we're clearly running out of time. But I'm happy to take any questions from you. Thank you.
Thank you for your talk. Going back to your first picture with the semantics in the middle and everything you derived from that.
Yeah. That's a K picture we use like all the time.
So I definitely agree that the interpreter can be derived, but things like symbolic executor, compiler, program verifier,
yes,
these things you want, for example, optimizations so that your compiler will produce code that runs fast or your symbolic executor runs fast. And these things you can't really derive from formal semantics, or then you have to modify your formal semantics and then the artifact becomes unreadable. What's your experience with that?
So yeah, thank you for the question. That's a very good question. So I think that another theoretical breakthrough of K it shows that you can actually do formal verification using an operational semantics. And the foundation there is called reachability logic. Okay, so I know that when talking about formal verification, people think about Hoare logic or Hoare, logics like Hoare logic. But if you think about it, Hoare logic is not a logic, it's a design pattern. It basically tells you if you want a formal verifier of your language, design a logic, right? So you have a Hoare logic for each and every language. Reachability logic, on the other hand, is a language parametric logic. It takes a formal semantic, it takes the operational semantics of a language as input, and it gives you sound and relatively complete reasoning of formal verification.
I mean, I understand it's possible to do it,
yes.
But will you do it as well and as fast as a native verifier?
Oh, the performance.
Yes.
So I think performance cares. Performance is definitely so on interpreter, right? So performance, we are currently 1 order of magnitude slower than a handwritten interpreter. Verifiers, I don't think performance of a verifier matters that much because it's slow anyway, and it's and you do it once and for all for a language anyway, right? So for example, if I can spend half of my day prove my very important program, I'll be satisfied. The point is the usability. How fast can I get a trustworthy verifier for my language? Do I need to like design a whole logic from scratch, or I have something off the shelf to use?
So we'll have 2 questions from Rob and Conrad.
Yeah, not quite a question, more a response to what you said earlier about Hoare logics being a design pattern. I mean, there are Hoare logics where you just plug in an operational semantics and you get a Hoare logic, right? That's totally possible. Iris is an example of that. Mm-hmm. So this is, I mean, you can, given an operational semantics, derive all sorts of logics. But then also what we do in Iris is typically, that's not the logic you want to use. You want to have some nice reasoning principles on top of that. I don't know, do you have support for then adding these things and checking them, or I wonder how you're dealing with getting proper domain-specific reasoning principles?
Well, could you be more specific, adding what type of things on top of?
I mean, the standard thing is you want to have some sort of nice separation logic to reason about programs with a heap, because you need framing to do any kind of compositional reasoning. If you have more interesting structure in the heap, if you model all of C, you have fun things like sequence points, and you probably want to have custom reasoning principles which hide the sequence points from you, so that you can pretend they don't exist, and it's all just separation, and you just move up the stack from there.
So I think along the separation logic line of work, so there's some very interesting theoretical work, but I think on the engineering side, no, frame reasoning is not natively supported by K, and the reason for that is we think the frame rule as a property is a blessing of a language. It's not something universal, right? So it's actually a property of the semantics of a language. So because my language is designed in this way, I can prove the frame rule as a lemma. But there's no way for a framework to kind of take that for granted, right? Because there are clearly languages out there. I can design a language which don't have the framing property. So that's what makes it a bit challenging. I acknowledge that to do framing in K, because K faces all the languages. So somehow framing is something you have to do. It's a property you prove about your language, and then you can somehow take advantage of that. So we've not done much on that on the engineering side, but we've started to establish the connection between separation logic and K. On the theoretical side, I can point you to some interesting papers if that helps. Yes.
Okay, thanks.
Yeah.
So with respect to your comment that reachability logic gives us a generic way to derive these things from a semantics, if I'm understanding correctly, this does require your semantics to be stated in terms of a term rewriting system.
Yes.
So what I was wondering was, do you ever feel there are any expressivity problems when you're trying to maybe specify parts of the semantics that aren't so neatly described by a term rewriting system? The main thing I'd be thinking of would be some kind of inductive type system, like maybe for a structurally typed language. Mm-hmm. I would expect normally things like the weakening rules that are involved in those wouldn't go into a term rewriting system very naturally.
I think yes. So basically the reachability logic can be plug and play. And actually, if you look at the proof, right, it's a sound and relative complete proof. And the way you prove that is it's complete, modular, all the static reasoning you want to do. So you can really put the, the inductive reasoning of data structures under the big bracket of like static reasoning. So I just prove like the equality of some properties about the static data, inductive data. And reachability logic only talks about the dynamic part of a program. So if you do that management, then yes, they can be embedded.
So you wouldn't, when you talk about these languages being specified, that doesn't include their type systems, or does it include their type systems?
It can include the type systems if your type system is part of a semantics. What I'm saying is that so basically you can integrate the reachability logic verifier with other means. Actually, as a matter of fact, we do have, like we use, for example, Z3 for built-ins. And you can extend that to like some static reasoning about inductive data types, because maybe that they are more efficient, performant, and so on. So yes.
Okay, let's take the other questions offline. Thanks a lot. We have
Happy
a
to.
coffee break.
Yes.
So please give him big hands. Thanks a lot.
Thank you.
And Matthew.